Well, the standard approach is basically what we do with the Shrp ice melting capacity test. You may be familiar with that. This shows you a photograph of a typical test plate. All we do is we take a tray of ice, we stick it in a freezer at a controlled test temperature, we apply de-icer to it. The Shrp method suggests applying 4.17 grams as a standard application rate. We give it some time to melt. We tip the tray up, let that melt drain into a corner. We withdraw it and measure it, and that's our ice melting measurement. Now, this is a good test from the standpoint that it's very intuitive and it's very real world. What could be more real world than putting a de-icer out on some ice, letting it melt, and seeing how much melt you get? So there's nothing wrong with the test method from that standpoint. The thing about the test, though, is that while it's fairly real world and intuitive, it lacks precision and it suffers from some inaccuracies. And these are due to the difficulty in recovering all the melt from the ice. You see here a close-up, again, that same test plate. And what you see is crystals of salt that have been distributed across our ice plate surface, and it's melting. And of course, what happens as those salt crystals melt is they start boring down into the ice. They bore into the ice, they make little wells, and melt gets trapped in those little holes. And melt can get trapped underneath the ice. It's impossible to get all of the melt off the surface of the ice. And so this introduces both potential underestimates of the total ice melting capacity. It also introduces variation in the test method, inconsistency. From test to test to test, I get different values because of the difficulty in recovering all of that melt. So what we wanted to do was to see if we could improve the accuracy and precision of this measurement. Because the more precisely I can measure differences between different de-icers, the better I can distinguish de-icers. So let me show you what I mean by that. So the approach that we took was to try and increase the total volume of ice melt that we were measuring. Our rationale was the following. Let's say that the uncertainty in your measurement when you're measuring the ice melt is plus or minus 1 milliliter. And then let's say your total ice melt is 2. Well, if that's the case, you're measuring 2 plus or minus, with an uncertainty of plus or minus 1, that's a 50% uncertainty in your measurement. On the other hand, if your total ice melt volume is 100 milliliters, now you're measuring 100 with an uncertainty of 1, your measurement error is only 1%. That's much better. If your measurement error is 50%, it makes it difficult to tell the difference between two different formulas. This formula has to be much different than this formula if I've got 50% uncertainty in each measurement. If I've got a 1% uncertainty in each measurement, I can probably distinguish the difference between de-icers that are maybe this far apart. So that's why we want to increase the precision of the test method. So what we looked at was trying to increase the volume of melt by two approaches, by using longer measurement times and going to higher application rates. So the standard test method calls for an application rate of 4 grams. We looked at 4, 8, 12, and 16 gram application rates. And this is what we saw. You see here a graph of the ice melting of plain rock salt at a temperature of 15 degrees measured over a period of 7 hours at 3 different application rates, 4, 8, and 12 grams. And I want you to notice a couple things. First of all, here's our measurement at 1 hour. 1 hour is the time that is suggested by the Shrp method, and of course it's also a time frame that this test is typically done in. Nothing wrong with that. It's entirely reasonable to make measurements over a period of 1 hour because, of course, often we want to understand how well that de-icer is going to work in a short period of time because we're going to have levels of service demands requiring us to get effectiveness in a fairly short period of time. So it's reasonable to measure ice melting after 1 hour, but for the purposes of understanding performance, it's instructive to look at what happens at longer times. And what we see is that the ice melting is far from complete after 1 hour, that we get more and more ice melting from salt. So here's where we need to be careful. If you assume that the ice melting you get after 1 hour in an ice melting capacity test is the true total ice melting power, you may be wrong. And certainly it's wrong in the case of salt. The second thing I want you to notice is that my ice melting capacity changes with my application rate. as I go from 4 to 8 to 12 gram application rates, my ice melting capacity, which is measured in melt per gram, is getting bigger.